Okay, in this first video, we're going to be going over the setup for exponential functions. So up to this point, we've only talked about linear functions. We haven't gone into any other type of function. So this is our first kind of new type of function that we're going to talk about. So consider this table we have here that's looking at years versus populations. So let me go ahead and start looking at this and try to see if it's linear. So if you notice, all of these years increased by 1, so they're all consecutive years. So the only thing I'd really have to check to see if it has a constant slope is to look at the change in the population. So that's why I have that third column there. We're going to find the change in population to kind of see if this might have a linear situation going on here. So if I find the change between these first two values, so 14.66 minus 14.235, I'm going to get 0.425, and there was nothing here. The change between the next two would give us 0.438. So it definitely seems like it's not going to be linear because those two don't even agree. But let's just continue this out. If we go between 2009 and 2010, the change in population is going to be 0.441. So definitely doesn't seem to have some constant slopes going on. 0.464, 0.478, and 0.492. So we definitely don't have any kind of constant slope going on here that we would need for a linear function, but there is actually a pattern that you might not be able to see right off the bat. So this does have a different type of pattern going on. So what we're going to do is we're going to consider the ratio between consecutive years, and we're going to take the ratio of the population. So let me look at the populations in 2007 versus 2008. So in 2008, we had a population of 14.660, and let me divide that by the population in 2007. So let me put off to the side, maybe a reminder that that's 2008, the population divided by the population in 2007. This is going to give us a pretty long decimal, approximately 1.0298559989. Now let's look at a couple other consecutive years. Let's go from 2008 to 2009 now. So from 2008 to 2009, well, in 2009, we had a population of 15.098. We're going to divide that by the population in 2008. 14.660. This is going to get us 1.029877217. And let's just take one more. Let's take 2010 versus 2009. So we have a population of 15.549 divided by the population in 2009, so 15.098. This is going to give us 1.029871506. Now, in full, those decimals don't agree, but we do have this kind of pattern where up to the first 4 decimal places, these do agree. So since they agree to, such a decent amount of decimal places, so since this matches up to 4 decimal places, we will say they are quote unquote similar enough. Now here, if you think about it, these populations might be rounded because they also are cut off as a decimal. So if we had the full population here, maybe these would match completely. But since they match up to 4 decimal places, that's pretty decent enough to say that they're essentially the same value, right? They're very close to being the same decimal. So we're going to say that this data has a constant factor, since all of these ratios agree up to 4 decimal places. So we have this relationship not in the change in population, but in the ratio of consecutive years for the populations. So we have a constant factor instead of a constant slope, and that's the big difference between a linear function and an exponential function. Linear functions have constant slope. exponential functions have a constant factor. Now, I'm going to take a little side note here for a second to try to illustrate this a bit better, I think. So say I had a table, you know, just 1, 2, 3, and then maybe let me jump to 6. And say we had 2, 4, 8, and 64. Well, if you note, if I go from 2 to 4, actually let me add in one more data set here. Let's put 6 over here and add in 4 for 16. If you note, between 1 and 2, 2 and 3, and 3 and 4, all of those numbers got multiplied by 2 to get the next y value. So to get from 2 to 4, I multiplied by 2. To get from 4 to 8, I multiplied by 2. To get from 8 to 16, I multiplied by 2. Now, I don't multiply 16 by 2 to get 64, but also notice that there's a gap between 4 and 6. This would also be a representation of an exponential function, because essentially what's happening in exponential functions is to get from one y value to the next, you're multiplying it by a certain number. And for it to be an exponential function, that number has to be constant. And it is actually going to be constant in this example as well. So it's easy to notice when it's consecutive x values. So for consecutive x values, it's kind of easy to see because you can just divide the one by the other, just like we did with the populations above. But what if we don't have, you know, for this example, consecutive years, for this example here, and also here, how could we know that this factor was actually what it was supposed to be as well? So let's kind of look at that really quick, because you still can find this factor even if you don't have consecutive years, consecutive x values. So let's go back to this population example really quick and forget about the side note that I've been looking at for just a second. Here's how you're going to be able to find the factor even if you don't have consecutive years. What you're going to do is you're going to find what we're going to call delta x. So this is going to be some x2 minus x sub 1. Now this is even going to work even if you have consecutive years. So you can still use this process even if you have consecutive x values. So you're going to find the difference in the x values that you're considering. And then what you're going to do is you're going to calculate that root of the ratio of the y values. Specifically, it has to be y2 over y1. Now also, I suggest letting x sub 2 always be greater than x sub 1. It just makes the root a bit easier because it will be a positive root. This still can work even if delta x is negative. It's just negative roots are more complicated to deal with algebraically. In a calculator, you can just kind of type it in. Also, in terms of putting these into your calculator, so kind of a note, calculator note. You can put in a root as that, whatever you want to take the root of. Then you can make it a 1 over that root power. So for example, if you wanted to take the 4th root of 16, that would be equivalent to saying 16 to the 1/4 power. So a lot of times it's easier to just type in the fractional power than actually finding the root button. But that's how you can type it into your calculator. So for instance, for this year example above, so let's look at, say, 2007 to 2009. Well, then delta x would be 2 because the difference between 2007 and 2009 is 2. So we'd want to be taking the square root of the population in 2009, which was 15.098, divided by the population in 2007, which was 14.235. Now, technically, the square root, when we have the square root, we don't need that little, that little 2 out front. We can just write a square root. But this would also give us 1.02988, 866, and it continues on. But it does still agree up to those 4 decimal places. And so say we take another example, say we go from 2008 to 2012. Well, the change in x there is going to be 4, so we'd want to take the 4th root of the population in 2012, so 16.491, divided by the population in 2008, so 14.660, would also give 1.298, and so on. So even if you don't have consecutive x values, we still can find this constant factor. And finding this factor is going to be something we're going to need to be able to do. So going back to this side note example really quick. So it seems like we're multiplying all of the y values by 2 to get up to the next piece. So let me triple check that this set of information from 4 to 6 also matches that. Well, the change in x between 4 and 6, so delta x in that case would be 2. So I'd be taking the square root of 64 divided by 16. Well, 64 divided by 16 is 4, and the square root of 4 is 2. So we still do have that factor of 2, so we would know that that data set is an exponential function with a factor of 2. So hopefully that kind of side note example makes it a bit easier to see, because we're working with numbers that are a bit easier to see that you're multiplying the one y value by something specific to get to the next y value. That's technically what's happening in this year example as well, but this side note example might be a little easier to see, so I'm going to kind of keep that off to the side. So now we've got to fill out a couple definitions. So we say that p is an exponential function of t with what we're going to call base a, if it can be written as p equals some p naught a to the t. So p naught is going to be called the initial condition, which is also going to be when t equals 0. So if you ever hear an initial condition and you need to find out when that happens, you can just let t equal 0. It's going to give you the same value. And a, while it's called the base, what a actually is a is the factor. P changes by when t increases by 1. So in my little side note example above, a would have been 2. In our year example, a was this 1.0298. I've also realized a small typo above. There should have been a 0 here, because it does turn out to be the correct decimal. I just wrote it wrong to begin with. But just going back to that really quick in case you picked up on that. So going back to this idea, so we have p naught a to the t. Now the a value, if a is greater than 1, we're going to have what's called exponential growth. And if a is between 0 and 1, we're going to have what is called exponential decay. Now, one very large note is that a does not equal 1. That is not a thing. You can't have an exponential function where a is 1. This would actually turn out to be linear. So if you're ever looking at a data set and you think that the a value would be 1, you see that you just multiply each y value by 1. That's not an exponential function. It would actually be considered linear. Also, our a value is also essentially equal to 1 plus r. Now, r is going to be the decimal representation of a percent change. So we're going to have an a value and an r value. Now, when r is greater than 0, we're going to have exponential growth, which I'm just going to write as growth. So note that these two situations, a greater than 1, r greater than 0, mean the same thing. And then if r is less than 0, we're going to have decay. So again, we have that these two situations, r less than 0, a between 0 and 1, both represent decay. And the last bit here is the most common base is the number e, which is 2.71828. Technically continues on forever. I should put some an ellipsis there. It's kind of like pi. It just continues on forever. This is going to be called the natural base. Your calculator does have an E button and also usually an e to the x button. It kind of depends on your calculator where it is. So you can always Google your type of calculator, where is the E/e to the x button. Or I'm sure if you stare at it long enough, you should be able to find it because it is usually just, my calculator's getting blurred out. It is usually just on the main calculator piece. You don't have to click into any other setting to get it. So that's going to wrap up this video. In the next video, we're going to go through some examples with exponential functions and finish up 1.5 notes in a different video.